Good day, guys. Alright, so in this video what I want to talk about is single slit diffraction or single slit interference. In the previous videos we've talked about Young's double slit, we've talked about thin films, and even prior to those two we talked about Huygens principle. And it's in this particular um, example that we'll really see how strong Huygens principle really is. Okay, so let's consider the case for a single slit. So what we have here is a single slit of with a slit width of A, right? And then we have just a horizontal line representing the middle, you know, A half. So these three dots are in the first half, the next three circles are in the second half, right? And then I have the screen on the right hand side. Okay, so what we have here, and I'll explain a bit about the general approach. The general approach would be we choose a point on the screen, and then we talk about two different light rays sourcing from two different points of the slit. So, and then what we need to do, differing from our approach to the Young's double slit, would be we would consider the minima, or in other words the dark fringe, because you'll have a central bright fringe, and then we will be able to work out the width of that central bright fringe from where the dark fringes are. Okay, so we are focusing on the dark fringes right now. Okay, so let's say what would be the approach, right? Let's say I take the first point, right, the top one right now, as the source for the first light ray, and then I shift it, I shift it by a half, and then that becomes the source of my second light ray. Okay, and then I say that it is at this point, right? I'm just going to use ym. It is at this point that they form a minima, okay, or a dark fringe, right? So as you can see, this is no different than the Young's double slit case, right? So I have the phase difference here, right? You can have the phase difference there, okay? So if that is the case, then I can also write the same as I have written for Young's double slit, okay? Which is the distance between them is just a half, and then sine theta, right, equals to half a lambda. Half a lambda because they form a dark fringe. Dark fringe, right? So what I'm left with is a sine theta equals to lambda. Okay, so the thing about this is that it is immediately you can immediately translate this into all other cases as well. If I chose, for example, if I chose the second one, then it would correspond to the fifth one. The second and the fifth one will form a minima at ym. If I choose a third one, the third point, then it will form a dark fringe at ym with the sixth one, or the last one here. So all of these two pairs, right, they combine or they interfere with each other destructively at ym. Okay, so what I can do is that I can generalize that. So that I have a sine theta equals to m lambda, m being the order of the order number for the dark fringes. Okay. All right. Again, here we use a small angle approximation where we have sine theta is approximately tangent theta, which is approximately just ym over L. Here, I'll label this L, ym over L, and what I'm left with is a ym over L equals to lambda. Sorry, m lambda. So the position of those dark fringes is going to be m lambda L over A. As simple as that. Okay? Alright, so once we understand this idea, what we can do is we can apply it, or we can try to apply it to a question, a work example. Okay, so here's the work example that we can work with. All right, I have a beam of monochromatic green light that is diffracted by a slit of width 0.55 millimeters. All right, okay, so I have A equals to 0.55 times 10 to the power of negative 3 meters. Okay, the diffraction pattern forms on a wall 2.6 meters beyond the slit. So I have L equals to 2.06 beyond the slit meters. The distance between the positions of the zero intensity means that the dark fringes, yeah? Dark fringes on both sides of the central bright fringe, sorry, on both sides of the central bright fringe is 4.1 millimeters. Okay, calculate the wavelength of the light. All right, so the last part doesn't give us an exact variable to pinpoint it. So what we need to do is we need to redraw what we have, which is the center, which is just a single slit, right? And then let's just have a point from here. This is my first zero intensity. Okay, and then I will have another one down here, zero intensity again. On the top one, I can label it as m equals to 1. Then at the bottom one, I can have m equals to negative 1. Okay, so that's just the middle part, right? So I can find the position from ym, for ym, right, as well as here. And because they're symmetrical, I can just multiply that by 2, right? If I have ym equals to lambda L over A, m being 1 here. If I double that, I will find this distance. Let me just change colors. Okay, so this distance, let's call it D, right? So D is going to be is simply going to be 2ym, right? Which is just 2 lambda L over A. And this 4.1 millimeters is actually the value of D. Okay, I can rearrange that now so that I have lambda equals to dA over 2L. Okay, all right, so I can substitute the values. So D is 4.1 times 10 to the power of negative 3. A is 0.55 millimeters, so 0.55 times 10 to the power of negative 3 again. And then I have to multiply by with 2.06. Okay, and that will give me a value of approximately 547 nanometers. And that is my final answer, which is the wavelength of the light. So what is D exactly? D is actually the width of the central bright fringe. Okay, so I'll just write a note there that D is actually the width of central bright fringe. Okay, and that is how you can reverse engineer it as well to find the width of the central bright fringe. If I give you some light of some wavelength, right, and then I have a single slit of some width, some distance from the slit, right, you can work out the width of the central bright fringe using the same equation and using the same symmetry, which is just double of ym. Right? Okay, so that is all from me in this video. I'll see you in the next one. Thank you.